A very good morning. My name is Xia Kai-chun. My matrix ID is KA24071, and I'm here with my group to talk about designing for a sustainable future. As Malaysia's population continues to grow, currently sitting at 15.13 million, the demand for buildings continue to rise. While development is essential, Malaysia's power sector emissions were seen growing exponentially in the last 2 decades due to an increase in fossil fuels to meet rising demands. Burning of fossil fuels, in particularly, are the largest contributor to the emissions of greenhouse gases, primarily carbon dioxide. Carbon dioxide gases traps heat in the atmosphere, causing global warming, which can lead to habitat loss and eventually an extinction of a species. Hence, smart technologies, including artificial intelligence, sensors, and automation, should be integrated into buildings so it can intelligently monitor and adapt to real time conditions, significantly improving the energy efficiency. The average monthly household energy demand in Malaysia by the year 2018 is around 559.24 kilowatts hour. Most of the energy contributions are from daily household applications, such as refrigerators, around 49%, air conditioners, around 90%, and more. This results in the average monthly electrical fee of 192 ringgit and 57 cents. Obviously, energy consumption can be reduced further by implementing a tiny machine learning device, TinyML. This is a small device connected throughout the house. It tracks all the movement of energy and can help save energy and electricity bills up to a reasonable percentage. My teammate, Ng Zhiyang, will provide further explanation about this product. Thanks.
Thank you, Kaijun. My name is Ng Ziyang, not Metri, KA24072. I will present what is Tiny Machine Learning. Tiny Machine Learning, which is TinyML, refer to running machine learning model directly on small, low-power microcontroller devices. Enable on-device analytics in the milliwatt power range, supporting always-on use case of battery-powered gadgets. So, what is the use and the function for TinyML? Typical TinyML hardware are compact microcontroller board equipped with sensors. Developable train ML model on PCs and the clouds, then deploy optimized model onto the devices. The result is real-time on-device interference without data transmission. By embedding intelligence in Tiny, always-on sensors, TinyML unlock AI of everyday tasks previously too compute intensive. For example, as you see in the slide, TinyML used in a smart home for daily use, TinyML computer, electricity meter, motion sensors, water flow sensors, and gas sensors. For the sustainable future, TinyML advanced sustainability across three dimensions, which are environmental, social, and economic. For environmental, TinyML reduces energy consumption by shifting interference from the cloud to each device. For the social, TinyML empower community, especially those in remote or resource-limiting regions. For economy, TinyML use inexpensive microcontroller instead for costly cloud servers, reducing both capital and operating expenses. There are few SDGs related to the sustainable future, which are SDG 11, 12, 13, and 15 as shown in the slide. So, the further information will be presented by my next teammates. Thank you.
Hello everyone, I'm Kugan and my metric ID is KA23088, and today I'll begin my exploration on the sustainability benefits of the TinyML solution from the environmental, social and economic perspectives. From an environment perspective, TinyML improves energy efficiency through a low power edge processing. This reduces dependencies on the cloud computing and continuous data transmission, leading to lower electricity consumption and reduced carbon dioxide emissions. The system can also detect gas leaks, water leakage, and inefficient appliances at early stage. With real-time monitoring, resources are used only for the when necessary, preventing wastage and supporting environmental conservation. Next, social perspective. From this social perspective, TinyML enhances safety and comfort for building equipments. Early hazard detection helps prevent accidents and create a safer living environment. Automated control of lighting, cooling, and ventilation improves indoor comfort while reducing manual effort. Since the system operates without constant internet access, it is suitable for rural and undeveloped areas, and lower energy consumption also results in reduced electricity bills, promoting social equity. And finally, economic perspective. From this economic perspective, TinyML provides a cost-effective solution of smart building management that use low-cost sensors and microcontrollers with minimal power requirements. Predictive monitoring minimizes maintenance needs, reduces downtime, and extends equipment lifespan, resulting in long-term safe cost savings and cost supporting circular economic practices. Next, I'll be explaining about how the TinyML support system applies the four material classifications that we studied in BMM 1133 material science. The system effectively utilizes metals, polymers, ceramics, and composites to achieve durability, efficiency, and sustainability. First, metals such as copper, aluminum are used in wiring, circuit boards, and sensor connections due to their excellent electrical conductivity and durability. Their long lifespan reduces frequent replacement, and their recyclability helps minimize environmental waste. Next, polymers. Polymers are used in sensor buildings, insulation layers, protective casings, and flexible cables. These materials are lightweight and corrosion resistant, reducing material usage and manufacturing energy. They also provide electrical insulation and moisture protection, improving device safety and reliability. Next, ceramics, which are applied in components such as capacitors, substrates, and gas sensors. Their high thermal stability, chemical resistance, and excellent electrical insulation allow reliable operation in harsh environments, improving durability and reducing electronic waste. And finally, composite materials. Composite materials are used in structural enclosures and sensor assemblies. Their high strength to weight ratio makes devices lightweight yet mechanically strong, reducing material consumption and enhancing long-term performance. In conclusion, the TinyML solution combines sustainable technology with appropriate material selection that reduce environmental impact, enhance social well-being, and remain economically viable, fully aligning with the principles that we taught in BMM 1133 material science. Thank you.
Good morning. I am Nicholas Lin Ziwei and my matrix number is KA24085. I'm here to present about the implementation and discussion of TinyML-based systems. The implementation of TinyML smart building system is feasible as the case study demonstrates a reduction in household energy consumption from 42 kilowatt-hour to 90 kilowatt-hour every 2 months, which reached the new minimum and maximum energy saving price approximately 170.89 ringgit and 146.13 ringgit. This indicates that the TinyML system can be realistically applied to reduce energy demand and also operating costs. TinyML system enable on-device processing with the use of low-power microcontrollers, reducing dependency on cloud infrastructure. Its implementation is visible for continuous monitoring and control of building systems such as lighting and HVAC, which can enhance energy efficiency while maintaining low operational costs. There are several challenges and limitations for TinyML system. The first challenge is limited computing power, and TinyML runs on microcontrollers with limited memory and processing capability. And the second challenges is model accuracy trade-off. Smaller models of TinyML may reduce prediction accuracy compared to the cloud-based AI. And the third challenge is technical setup and maintenance. TinyML requires expertise to train, deploy, and also update TinyML several years. And the last challenge is scalability and also integration. By integrating multiple TinyML systems into large building will be very complex. In conclusion, TinyML-based systems allows for intelligent real-time energy management because it is able to process information directly on low-energy devices. Additionally, it cuts down on energy costs as well as cloud computing, making it an appropriate technology for smart, sustainable buildings. TinyML is applicable despite its lack of scalability computing capabilities. And this is the end of our presentation and also our project. Thank you.